Imagine controlling a swarm of invisible particles, each with a unique path and destiny, dictated by the laws of physics in a digital cosmos. This isn't a scene from a futuristic movie, but a daily scenario for engineers using the Discrete Phase Model, or DPM, in ANSYS Fluent. DPM allows us to predict and visualize the behavior of particles in a flowing medium, a crucial aspect in industries ranging from pharmaceuticals to aerospace. Through this comprehensive guide, you'll not only learn to master DPM, but also harness its full potential to elevate your engineering solutions. DPM stands as a revolutionary approach in computational fluid dynamics, allowing engineers and scientists to simulate and analyze the movement of discrete particles in a fluid flow. This model is pivotal for industries where small particles play a crucial role, such as in the dispersion of pollutants in the environment or the mixing of ingredients in pharmaceuticals. The core of DPM lies in its ability to track the fate of thousands, sometimes millions of particles as they travel through different mediums. By applying Newton's laws of motion to each particle, DPM provides insights that are critical in optimizing processes and improving product quality. Understanding DPM is not just about mastering a software tool, it's about envisioning the interplay between particles and fluid flow, which can often be counterintuitive. For instance, the trajectory of particles in a cyclone separator might reveal unexpected patterns of accumulation and erosion, crucial for industrial applications. Before diving into the complexities of DPM, one must first become acquainted with ANSYS Fluent. This powerful software offers a robust platform for carrying out detailed simulations, but requires a thorough understanding of its interface and capabilities. The initial setup involves configuring the working environment, which includes selecting the appropriate solver settings, materials, and models. It's crucial to ensure that all parameters align with the physical scenario you intend to simulate to avoid skewed results. A significant part of the setup is the meshing process. In DPM, the quality of the mesh can greatly influence the accuracy of particle tracking and trajectory prediction. Hence, spending time perfecting the mesh is an investment in the reliability of your simulation outcomes. The heart of DPM simulations in ANSYS Fluent lies in its detailed settings and configurations. The software provides a myriad of options, each tailored to specific types of particle behavior and interactions. The Discrete Phase Model dialog box is where most of the configuration happens. Here, engineers can define particle properties, including type, inert, droplet, combusting, size distribution, and material properties. Each selection drastically influences the simulation results, making this step critical. Injection types and their configurations play a pivotal role. Whether particles are injected through a surface, at a point, or along a line affects their initial distribution and subsequent dynamics. Understanding these options allows for the simulation of complex scenarios, such as fuel sprays in engines or pollutant dispersion in rivers. Simulating real-world scenarios. Spraying mechanisms. Spraying mechanisms are complex systems where discrete phase modeling, or DPM, can provide significant insights, especially concerning droplet breakup and evaporation. Setting up such simulations in ANSYS Fluent involves a detailed understanding of physical models and boundary conditions. The process begins with defining the type of spray, the properties of the liquid, and the operating conditions. This setup requires adjustments in the particle injection settings to accurately mimic the actual spraying process. The choice of breakup model, like TAB or wave, is crucial as it determines how droplets fragment under different conditions. Similarly, including evaporation models affects the temperature and phase change behaviors of the droplets, essential for applications like paint sprays or fuel injectors. Wet combustion simulation is a sophisticated application of DPM, where the interaction between combusting particles and the surrounding fluid needs precise modeling. This setup is crucial in industries like energy, where fuel burning efficiency and emission control are paramount. The simulation starts with the definition of particle properties, such as initial temperature, composition, and phase. Setting up the correct combustion and thermal models is key to tracking the particle's heat release and its impact on the surrounding fluid. Analyzing the results from wet combustion simulations helps in optimizing burner designs and improving the efficiency of fuel use. It also provides insights into pollutant formation and ways to mitigate them, essential for complying with environmental regulations. Erosion modeling is another critical application of DPM. In industries like oil and gas, understanding how particles impact and wear down equipment can lead to better materials choice and design improvements. The setup involves defining the material properties of both the fluid and the particles. The erosion model in ANSYS Fluent allows users to simulate the impact of particles on various surfaces, predicting areas of high wear and potential failure. This type of analysis is crucial for prolonging the life of equipment and preventing costly downtimes. It also helps in designing more robust systems that can withstand the harsh conditions often encountered in industrial processes. In the context of healthcare, DPM can be utilized to model the behavior of airborne particles, such as those involved in the spread of respiratory diseases. This application is particularly relevant in designing hospital ventilation systems or studying the effectiveness of air purification technologies. The simulation process involves setting up particle injections to mimic coughs or sneezes and analyzing particle trajectories within different room configurations. Adjustments in airflow patterns, temperature, and humidity can significantly affect particle behavior, insights that are vital for infection control. Understanding the dispersion and settlement of infectious particles helps in creating safer indoor environments, crucial in preventing the spread of diseases in healthcare settings and beyond. This comprehensive guide to mastering DPM in ANSYS Fluent equips you with the knowledge to tackle complex particle dynamics scenarios across various industries. By understanding and applying these techniques, engineers can ensure more efficient processes, safer products, and ultimately, a deeper understanding of the microscopic forces at play in their fields. Imagine controlling a swarm of invisible particles, each with a unique path and destiny, dictated by the laws of physics in a digital cosmos. This isn't a scene from a futuristic movie, but a daily scenario for engineers using the Discrete Phase Model, DPM, in ANSYS Fluent. DPM allows us to predict and visualize the behavior of particles in a flowing medium, a crucial aspect in industries ranging from pharmaceuticals to aerospace. Through this comprehensive guide, you'll not only learn to master DPM, but also harness its full potential to elevate your engineering solutions.